The fundamental counting principle is really not a very difficult concept. All we have to do is multiply our options together. I do want to explain why we do that, and I also want to just point out some of the intricacies of it and the fact that it's easy, but we have to read the problem very carefully. So let's jump in. You're ordering ice cream and you have these options. You could get a cup or a cone. You can have 3 different flavors, chocolate, vanilla, or strawberry, and you can have different toppings, sprinkles, walnuts, or chocolate syrup. So let's just read really carefully. Assuming you order a cup or a cone, 1 flavor of ice cream, and 1 topping, how many different ways of ordering ice cream are there? So here's one way to represent it, and you don't have to do it this way, and this is the long way. We'll only do it this one time. We could have a cup or we could have a cone. So cup, cone, and we could do that. And then once we do that, we can split it into chocolate, vanilla, and strawberry. So chocolate, vanilla, strawberry, and then chocolate, vanilla, strawberry, chocolate, vanilla, strawberry. And then if I get chocolate, I could have sprinkles, walnuts, or chocolate syrup. If I have vanilla, I could have sprinkles, walnuts, or chocolate syrup. If I have strawberry, I could have sprinkles, walnuts, or chocolate syrup. See how this gets really cumbersome really quickly? And then if I have a cone in chocolate, I could have sprinkles, walnuts, or chocolate syrup. If I have a cone in vanilla, I could have sprinkles, walnuts, or chocolate syrup. If I have a cone in strawberry, I'll have sprinkles, walnuts, or chocolate syrup. Okay, we are not going to do that again. It's actually called a tree diagram, and it's just, it gets really messy really fast. But the real answer actually is how many different ways of ordering are there, and here they are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So the final answer is 18, but here's a faster way. I just wanted you to see the representation that some people use. We won't do that again. Here's the other way of doing it. We have 2 options when it comes to how we're going to keep our ice cream in one place. Is it going to be in a cup or in a cone? And then we're going to have flavors. So let's just put here, and we're going to be like cup or cone. And then over here, we're going to have flavor. And we're going to have 3 different flavors. And then we're going to have 3 different toppings. And so it's 2 times 3 times 3, and that's where the 18 comes from. Much faster. We just have to read very carefully because the next one looks the same, but it's different. And we are definitely not going to do that on the next one because it splits even further. We'd have to go even further. Assuming you order a cup or a cone, so let's just kind of start it this way. So cup or cone. So we have 2 options there. We're going to multiply our options together. And then 1 flavor of ice cream. So we're going to get 1 flavor of ice cream, but we have 3 options. So we're multiplying our options together. Even though it says 1 flavor, I have 3 options. So here's my flavor. And you don't have to label these down here. I am because I'm explaining things. And then you get 2 different toppings. So now we have a couple things going on here. We have our first topping. And then we're going to have our second topping. And for our first topping, we have 3 options, sprinkles, walnuts, or chocolate syrup. Well, once you choose a topping, and it said 2 different toppings, so if I choose like sprinkles, then now I have 2 options remaining. I could get walnuts or chocolate syrup. Or let's suppose I choose for my first topping, I get walnuts. Now I have 2 other options, sprinkles or chocolate syrup. So there's that, and we're just going to do 2 times 3 times 3 times 2, and that is 36, which kind of makes sense because the last one was 18, and it went up to here, and then we double that, and we get 36. Okay, just read carefully. So let's go a little bit faster now. On a standard North Carolina license plate, there are 3 letters followed by 4 numbers. How many different license plates are possible? So letter, 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 letter. I'm not going to write this every time. Letter, followed by 4 numbers. Number, 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 number. There's a dash in the middle, but if I do that, it would look like subtraction, so let's not do that. So a number goes here, number goes here, number here, and number here. And then how many different license plates are possible? Well, let's go back to the instructions at the very top. Multiply your options together. So let's multiply our options together. There are 26 letters in the alphabet. If I use a letter, I can use 26 for the next as well. And I use another letter, and then I have 26 more options. By the way, I'm using 26, 26, 26 because it never said I couldn't repeat a letter. That's actually going to happen on this one. All right. And then how many different license plates are possible if I have 4 numbers here? So 4 numbers, well, 4 single digit numbers. And so anything from 0 to 9 works, which is 10 digits. and then 10 digits, and 10 digits, and 10 digits. Now, good luck doing this one in your head. However, you can get at least part of it in your head. Let's be real honest. You know what 10 times 10 times 10 times 10 is. That's 10,000 right there. That would be a 1 with 1, 2, 3, 4 zeros. Just throwing that out there. So whatever it is, it's going to be something times 10,000. So we grab a calculator, and we're going to type it in, and this is why we have exponents. So clear that out. 26 to the third times 10,000, or 10 to the fourth, either way. And we have this ridiculous number here. So let's put commas in the right place. Right there, 175. There are 175,760,000 different possible license plates in North Carolina. That's a lot. All right, how many possible license plates are there in North Carolina if you are not allowed to repeat a letter? So same setup, but different numbers. So letter, 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 number, 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 number. And I'm not going to write that over and over because that takes a lot of time. So I am not allowed to repeat a letter. So let's suppose you want to use the letter A. Well, you had 26 options, but you picked a letter. You picked the letter A. Well, now you only have 25 options. And now you've used an A and an M. So you use an A and an M. I'm using my initials, by the way. An A and then an M. Well, if I've crossed out 2 letters of the alphabet, now for my third letter, I only have 24 options. That's an idea that's going to come in handy. There are times where we just count down. And then it did not say I couldn't repeat a number, so I couldn't have like 7777. That would be okay. 10, 10, 10, 10. 10 options here, 10 here, 10 here, 10 here. Again, I don't know what this is, but I know that's 10,000. And we will type that in. This won't take but just a second. So 26 times 25 times 24 times 10,000. And it is, let's put our commas in the right place, 156 million. Notice that it's less than the previous answer, 156 million. It's less than the previous answer because we've begun to limit our options. So the more you limit your options, the lower the number of possibilities it's going to be. So let's do number 5. How many possible license plates are there in North Carolina if you're not allowed to repeat a letter or a number? So again, same setup. Letter, 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 and I can't repeat, so I have 26 options. I choose a letter, now I have 25 options, and then I choose a letter, and then I have 24 options. Okay, then number, 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 and I'm not allowed to repeat a letter or a number, so I have 10 options for the first digit. And then once I choose my digit, like I pick a 7, well, I can't use a 7 again, so now I only have 9 options. And then I choose another number, and now I only have 8 options. And then I choose another number, and I only have 7 options. So there we go. We'll multiply that. By the way, I don't know the answer, and this is clearly not 10,000 here. But it's going to be lower than that because we continue to restrict our options, the number of options that we have. So this won't take but another second. 25, 26, 25, 24, 10, 9, 8, 7. Just type it carefully. And now we are down to 78 million. 78,624,000 options. All right, let's continue working out a few of these. They don't get trickier. You just have to read more carefully. Let's flip this paper over, see what we have. 5 people are running a race. Their names are A, B, C, D, and H. I did that on purpose just to make us mad. And how many different ways can they finish the race? And we're going to assume there is no tie. So we are going to have 5 people, and they are going to run a race. And we can have a first place, a second place, a third, a fourth, and a fifth. So here's first, second place, third, fourth, and fifth. And I won't get a first place winner. Well, when I'm waiting for somebody to cross the finish line, there are 5 people that could cross the finish line first. So we have 5 options. Now, once somebody, we'll pick Herbert just because. Once Herbert crosses the finish line, now I'm waiting on the second person to cross the finish line, and we have 4 options. And then once Carl crosses the finish line, I'm making this up as I go, we have A, B, and D I'm waiting on. And so we have 3 options. And then we have 2 options. And then we're just waiting on that last person to get there. So there you go, 1 option. And we multiply 5 times 4 times 3 times 2 times 1, 120, by the way. And That's how many different orders they could be in. If you wanted to waste your time, if you're ever bored, you can list them in order. You could be like A, B, C, D, H, A, B, C, H, D, A, B, D, C, H, and you can do it. There will be 120 different ways you can arrange those if you're ever bored. I do want to introduce you to another mathematical symbol, and this is on Desmos, desmos.com/calculator. And anytime you need to figure out stuff like this, you could just type it into Desmos. But it's this right here. It's 5 and then an exclamation mark. And you're like, well, that looks like 5. It's actually not. This is called factorial. And we use it a lot, actually. We use it in a situation like this where we need to take a number, an integer, and then multiply all the way down to 1. So if I would have had the same problem, but it would have been like 17 people are running in a race. I don't want to figure out 17 times 16 times 15 times 14 all the way down to 1. Ain't nobody got time for that. So this is a lot faster if you have a big number. And the numbers get really big really fast, by the way. Like 17 factorial is huge, 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 which means we could not list them in our spare time. But that's what that means. So 5 factorial is the same as that. Just in case you care, I do want to show you what that is. If you're on the calculator, you could press math and go to probability, and there's your exclamation mark right there. So I'm gonna do 5, and then just showing you. Or you could just do the exclamation mark on Desmos. And 120, that's it. 5 times 4 times 3 times 2 times 1. All right, let's do this. George is creating a game in which each turn involves flipping a coin. Okay, all of a sudden I'm thinking, oh, we have 2 options. Rolling a 6-sided die, okay, 6 options, and then spinning a spinner with 5 equal-sized spaces labeled A through E. So whatever this game is, it sounds ridiculous, but every turn you're gonna flip a coin, roll a die, spin a spinner. How many different possible outcomes are there in each turn? I don't know. Let's figure this out. I wish I had some directions. Oh, why don't we multiply our options together? So let's do that. Let's multiply our options together. And I have 3 things that are happening. I have a coin, I have a die, singular for dice, and I have a spinner, and you're probably way ahead of me on this one, and that's okay. Coin, 2 options. Die, 6 options. Spinner, in this case, 5 options. We'll do this one in our head. 2 times 6 is 12, times 5 is 60 different ways we could get a different outcome. Now, if you wanted to bore yourself to death, you could draw, this would be fun. You could draw that. You could be like, I flip a heads, you get a tails, and then 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then 5 options for each one. Eventually you'd have 60. Okay, this one's based on a true story, by the way. These are some coworkers of mine and one former coworker. Tim, Adam, Lynn, and Marita are lining up for lunch in the teacher's lounge. How many different orders can they line up? Okay, here's the real story. We found out that there was, I think it was like ice cream or something in the teacher's lounge, or it was tacos, or I forgot what it was. Anyway, we found out it was there, and we were running. We're like, hey, there's tacos, and we're running down the hall. Well, I have the longest legs, so I may have come in first, although I was trying to be a gentleman, so I may have let Marita go. Anyway, beside the point. How many different orders can they line up? It's the same as this one, actually, only it's not a 5, it's a 4. So the long way is 4 times 3 times 2 times 1. So I have 4 people that could come in first place. Once we have a first place winner, we now have 3 options. Then we have 2 options. Then we have 1 option. I'll save you the trouble. It's 24. However, if this number would have been enormous and you really don't want to type 4 times 3 times 2 times 1 or like 17 times 16 times whatever, you can do this. Okay, totally random story that is somewhat related to this. When my niece turned 6, I got her a birthday card. And I wanted to find the exact right birthday card, and it said this. And I gave it to her, and she's like, I'm not 3. And I was like, oh, but that's not 3. That's 3 factorial. I was such a nerd. I am such a nerd. And so when she turned 6, so it was like 3 times 2 times 1, which was 6. There you go. When my grandfather turned 100, you're probably like, just stop and teach the lesson. I'll tell you in a minute then. How many different possible outcomes are there if you spin 3 spinners? Spin 3 spinners. Each spinner is labeled with 4 colors. He actually hasn't turned 100. Let me start the story over. Spinner 1, spinner 2, spinner 3. He turned 96. I got him a card that said happy 100th birthday, and I cut 4% of it off. So it was like this whole card, and it was like happy 100th birthday. But I measured it, found out how big it was, and then I cut 4% of it off, so it would be like 96% of a 100th birthday card. Anyway, when he turns 100, I'll give him the rest of the card. I still have it somewhere. How many different possible outcomes are there if you spin 3 spinners? I don't know why I told you that. Each spinner is labeled with 4 colors. So I have 4 options, 4 options, 4 options. Sorry to waste your time telling random stories about birthday cards. 4 times 4 times 4. And there you go, 64. Not too hard. Just read it carefully. All right, here goes. Sarah is going to pick out an outfit. She can choose from 4 pairs of pants. Oh, there we go. Pants right here. 8 shirts. 3 pairs of shoes. 2 belts. We're going to assume that either they all match or this individual does not care if they match or not. So here goes. 4 pairs of pants, 8 shirts, 3 pairs of shoes, 2 belts. Multiply them together. Just read it carefully. 32 times 3 is 96. 96 times 2 is 172. I'm going to double check that. 192, man, I was way off. I was trying to do way too much in my head. All right, 192 different outfits. Why did I get 172? Anyway, there you go.